kinematic quantities as vectors. So now in 2D, position, displacement, velocity, and acceleration are all vectors. And so I'm going to define these one by one. And I'm not going to talk about the units for them individually like I did before. The units are just the same as they were in one dimension. So SI units for position are meters. SI units for displacement are meters. For velocity, meters per second. For acceleration, meters per second squared. The only difference is we'll give these as pairs of components. Okay. So the first thing we have to define is the position vector. And to give position vector components, you must first choose an origin location and a coordinate system orientation. Okay, so this position vector is not defined until you make these two choices. Is that familiar at all? That's analogous to what we did in one dimension. These are like the 2D version of the zero position and the positive direction. So once you choose those, so say even before you choose them, you know, the object that you're tracking it exists, that it's going to exist whether you're there measuring it or not. But once you choose where the coordinate system is and the orientation of the X and Y axes, the position vector is the vector that goes from the origin of the coordinate system to the object. So this is the position vector. Another way to think about that is that the position vector components are the coordinates of the object. All right, well, usually we're going to want to know the position vector as a function of time. So what else do we have to specify? What else do we have to choose before we can define the position as a function of time? Yep, exactly. So if you also choose a time equals 0 instant, then you can represent the position vector as a function of time. And I'll write that. So there's the position vector. It's a function of time. And I'm going to break this down into an x component as a function of time and a y component as a function of time. Sometimes you'll also see it as px, the x component of the position, and py as a function of position. Those mean the same thing. So now we have to define the velocity vector. And just like in one-dimensional motion, the velocity vector as a function of time is equal to the time derivative of the position vector as a function of time. And the way derivatives work with vectors is you just take the time derivative of the x component and the time derivative of the y component, and those are the components of the vector. Now so the way to think about the position vector is, I said last time, is just basically to think about the coordinates of the position vector is just the coordinates of the object in whatever your coordinate system is. The way to think about the velocity vector is like this. Every vector has two pieces of information, two properties, the magnitude and the direction. The magnitude of the velocity vector, and you denote that with the absolute value of the velocity vector, is the object's speed. Yeah, dramatic. So if you think of the surface of think of the surface of Minneapolis as like a plane. As you're driving around, and if you chose a coordinate system on the ground, you could measure your velocity as a vector wherever you're going. And if you took the square root of the sum of the squares of your velocity components, that would give you the magnitude, and the magnitude would be what your speedometer says. Okay. And the other property a vector has is the direction. And that's the direction the object is moving at that instant. So if you have an object moving along, so let's say this is the path that an object is following, and let's say it's going this way. Okay. And let's say this is the object at the time we're interested in. The velocity vector is always tangent to the path. Okay. And I want to be try to be clear about something now. Notice that we've already, so now with this idea that the velocity is tangent to the path, we already have a way to draw two representations of motion. So there are two representations of motion that can look the same, but they mean very different things. The first one of those is a position versus time graph for a one-dimensional motion. Okay, so if you are dealing with one-dimensional motion and you have a position versus time graph that looks like, let's say that, and the place you're interested in is right here. Okay. Then the velocity is a number given by the slope. Yeesh. Okay, but now just to make this point, I'm going to use this same thing I just drew. Okay, so where's my, okay, so the second one, two, is the path of an object in 2D. Okay, so in the case that you're dealing with motion along a line or one-dimensional motion, this is a position versus time graph, and this entirely lives in math world. Okay, it's a graph. Okay, it's not showing anything about what the object actually does. The object's just going back and forth along the line. This, that looks exactly the same as that, lives in the actual world, and it's like taking snapshots really quickly, following the motion of the object as it moves through space. I can't really do that. But so this is the real world, this is math world, but they can look the same. So when you see a picture like this, don't just be like, I know I draw tangents and whatever. You got to know what you're looking at, okay? So this is the physical world. This is math world. And in this case, the velocity vector looks like that. The velocity is a vector and that vector is tangent to the path. Okay, so for an example, let's say that the position vector as a function of time is, well, let me do one that I can draw. So let's say the position vector is t and then t squared. So first, what's the velocity vector as a function of time? Second, what's the velocity vector at time, let's do 2 seconds. And then let's sketch the path. Let's sketch the motion in the physical world. So first, the velocity vector as a function of time is just going to be, take the derivatives of the two components. So this is going to be 1, 2t. And so now this is a function that'll give you the velocity vector at any instant. So at time equals 2, the velocity is 1, 4. And now, if this is our coordinate system, okay, so this is x and y, but this represents what's happening in the physical world, okay? The graph looks like this. So let's say this is 1, this is 2. So here's the path. And at 2 seconds, the object is at this location here. And the velocity vector is tangent to the path at that instant. So that's the velocity vector at time equals 2. Okay, and the velocity vector, when I break it up into components, I'm going to call the components Vx and Vy. Okay. And then the last thing we have to define is the acceleration vector. The definition of the acceleration vector as a function of time is the time derivative of the velocity vector as a function of time. Which is the second time derivative of the position vector. Now, acceleration, since this is a measure, what a time derivative tells you is the rate of change of something over time. Acceleration then measures how quickly the velocity is changing. And the velocity vector can change in two ways. So the velocity vector in 2D can change two ways. Its magnitude can change, or in other words, the speed can change. And or the direction can change. And so what I want you to notice is that that is fundamentally different from what the acceleration represented in 1D. So that's different than 1D. In 1D, any acceleration meant the speed was changing. Because there's no such thing as turning in 1D. All you can do is speed up or slow down along the line you're on. Okay. In 2D, you can have acceleration even with a constant speed. Okay. So there aren't too many things that are fundamentally different as you go from 1D to 2D and 2D to 3D, but here's something that's fundamentally different. We picked up this idea of turning now, okay? So how do you visualize an acceleration in 2 dimensions? So first, sketch the object's path. Then draw the velocity vector tangent to the path. Third, draw the part of the acceleration that's parallel to the velocity. If the object is speeding up, this vector A parallel is in the same direction as the velocity. I don't know what's going on with my pen here. And if the object's slowing down, A parallel is in the opposite direction of the velocity vector. Okay, so you can think of the acceleration as being made up of two parts. One part that's parallel to the velocity and determines whether it's speeding up or slowing down. And then a second part that's perpendicular to the velocity that determines whether it's turning. Okay. If the speed is constant, then there's no part of this acceleration that's parallel. Okay. Now, fourth, draw the part of the acceleration vector that's perpendicular to the velocity vector. So this is the direction the object is turning. If the path is straight, then A perpendicular is 0. Okay. And then the total acceleration is just the sum of these two pieces. So there's the parallel part and the perpendicular part. This is the one that affects speed change. And this is the one that affects turning. Okay, so let's say that the object's moving along this path from left to right. And let's say that we want to figure out the directions of the velocity and acceleration at that point. And we also have to know, and you can't tell from just looking at this picture, whether this is speeding up or slowing down. So let's say that it's slowing down. Okay. Again, if this was a position versus time graph of a one-dimensional motion, this gives you all the information you need to know whether it's speeding up, slowing down, because the velocity there is positive because the slope is positive. It's concave up, so it's speeding up at that point. But if this shows the path of an object in 2 dimensions, you need extra information to know whether it's speeding up or slowing down. One way that can be shown is if I mentioned that idea of taking snapshots. Say that you took a snapshot every 50th of a second or something, okay? What you would see isn't a continuous curve. you'd see a bunch of points, right? And depending on how close together those points are, it would tell you when it's speeding up and slowing down. If those points were getting closer together as time goes by, it's speeding up. If they're getting farther apart, no, it's opposite of that. If they're getting closer together, it's slowing down. And if they're getting farther apart, it's speeding up. Okay. Okay, so first let's draw the velocity vector. It's tangent to the path. So here's the velocity vector. And now we can start thinking about the acceleration. It's slowing down. So first we're going to draw the part of the acceleration that's parallel to velocity. Is it in the direction of velocity or opposite? Opposite. So there's a parallel. And now which way is it turning? There are two possibilities that are perpendicular to this line, that way or that way. So sort of up or down. Towards the inside of the curve. Yeah, always towards the inside of the curve. That's a good way to think about it. You can also just think of, does this curve, which side of that line does that curve go to as time goes forward? But so in this case, so there's a perpendicular. And now what do we know about the total acceleration? Well, we know the directions of these two, but we don't know the magnitudes. So we can't say exactly what the direction of the acceleration is, but we can say that if you add up a vector in this direction with a vector in this direction, you get something that's in between those two directions. So the total acceleration is going to be somewhere in this range of directions. Okay, so let me do another example. So for this one, let's say that an object moves with constant speed. And let's say it's moving in a circular path. Let's say clockwise. And we want to know the velocity and the acceleration at that point. The velocity is tangent to the path. Is it speeding up or slowing down? Neither, it's constant. So there's no parallel part of the acceleration. Which way is it turning? This way or that way? That way. Toward the center, yep. And so we have a perpendicular part of the acceleration like this. Now the total acceleration is the sum of the parallel and perpendicular, but the parallel is 0. So this is the direction, and it is actually the total acceleration. So if you have an object that's moving with a constant speed, in this case it's a circle, the acceleration is always perpendicular to the path. If you have something moving with a constant speed in a circular path, the acceleration is always towards the center. Let's do the one we're missing so far, I guess. So let's say that this car is speeding up. And it's going this way. So the path of the center of mass of the car would be like that. Okay. Let's figure out the directions, the velocity and acceleration. So In this case, at this point, the velocity is tangent to the path with it, which for a straight line is just straight along the path. Okay, it's speeding up. So the parallel part of the acceleration is the same direction as the velocity. Is it turning? No. So there's no A perpendicular. And so the total acceleration is just that parallel part. Which, this, if you were doing this calculations connected to this, you just do it as a one-dimensional problem. Why not? It saves you a little work or whatever. But this is how the two-dimensional stuff reduces down to what we saw in one dimension for something that's moving along a line.